to introduce myself. My name is Max. I work for ArangoDB, and in particular on the distributed part of ArangoDB. And thirdly, I should say that originally this talk was prepared by Ewout, who is here in the audience. And I'm shamelessly stealing everything he prepared, including slides. Well, I just gave them the ArangoDB corporate identity, but other than that, the content is his. And I stole his examples. And obviously, I'm using the ArangoDB Kubernetes operator, which essentially he wrote. So that's a project we are working on, and that's essentially what I want to talk about in this presentation. Very good. This means that my video is, if I stand exactly like this, it's exactly right. Okay, so this is a Kubernetes Meetup, so I can be very quick at this. What is Kubernetes? So just to be on the same side, it's essentially an operating system for compute clusters. Yeah. So it manages a cluster of computers in exactly the same way as the Linux kernel manages a computer and all the resources on there. So the Linux kernel manages disks and memory and whatnot, and CPU. And Kubernetes does this on the cluster level. So it manages nodes and CPUs on nodes and memory and so on. And the idea is that essentially as you start a process on a single server, now you start a process or a container or whatever on a Kubernetes cluster, and essentially Kubernetes takes care of scheduling it somewhere, giving the right resources and so on. Kubernetes was originally started within Google. And one should know that originally Google has a long history with container technology and was using another system internally, and is still using, called Borg. So they have very much experience with doing containerization and doing containers large scale. And that shows, if you look at what Kubernetes does, you see that there have been people involved which do it the second time round. And therefore, it has essentially won the battle of such containerization frameworks. And it has developed a very, very large community, and it is changing very, very quickly. So from each release to the next, there are so many new things in there that it is really nearly a full-time job just to keep track of what is going on in the Kubernetes world. Now, why does it matter? There's obviously others. There's Docker Swarm, there's whatnot, there's Mesos. But I think by now it is clear that Kubernetes is the winner. Yeah, it is by far has the largest growth, it has the largest community, it's open source, it's backed by the largest players and so on. So it is just winning, and it's considered to be cool. Yeah, so people like messing around with it, and so therefore, if you build an application, in particular if you build a distributed application, you have to run on Kubernetes. But it's also popular not just because it's cool and it's by Google and it's hype, but it is really helping. So in particular for DevOps, it is really, it makes their life simpler. It simplifies deployment, it simplifies operations, it's self-healing if configured properly. It has built-in monitoring, and it is built to do good monitoring. And so what we notice as a database manufacturer, people ask for Kubernetes support. Now, since we do a database, we obviously deal with state and with mutable state. And that turns out to be surprisingly difficult in a cloud environment, because managing containers at scale is comparatively simple if you can always get rid of them and start them anew and move them around and so on. But if they have state, then it's a lot more difficult. And so therefore, we are faced with a situation that we develop a distributed, stateful application. We want our customers to have it deployed easily. We must support something on Kubernetes. And we have to see how we can do that. And this talk gives you an overview about our efforts in this area. I should say that in the past we have first looked into Mesos and have spent a lot of time to make ArangoDB run on Mesos in a seamless way. And since approximately the beginning of this year, we concentrate more on Kubernetes, and by now we have something to actually show. So, I know you all know Kubernetes probably much better than I do, but let me just point out at least my understanding of what the fundamental concepts of Kubernetes are. You don't tell Kubernetes how to do things, you tell what you want. You say, deploy this and that, I need this and that, and Kubernetes goes away and deploys it for you. That's the idea. So what you do is you specify resources, you use resource specifications and deploy them via something called the API server. So you tell this API server, which is one of the things in Kubernetes, that you want something of this resource. And then in the background, something called Kubernetes controllers negotiates with this API server and makes sure that these things appear in the proper place. Now, what kind of resources are there? The simplest one is a pod. Yeah, and I think I can really be quick because probably you know all these details. A pod is essentially the smallest deployable unit. It's one or more containers which is running on some node. Obviously, containerization comes with isolation. You have some kind of network isolation, you have file system isolation, you have process isolation, and so on. And that is all done under this label pod. The second one should know is a service. That is essentially a resource you deploy to your Kubernetes cluster to make sure that a certain service is exposed somewhere on the network. Yeah? So in particular, if you, for example, run a pod which runs some kind of server, then you would additionally normally deploy a service which makes sure that you can contact that server in an easy way, which would be easy if it's just one pod. But if it's a more complicated system which needs load balancing or whatnot, then it's the abstraction for that is a service. The next one is deployment, and that essentially has facilities to ensure that something is up and running all the time. So, for example, you could ask for a deployment of one pod, which would start this pod in the beginning. But if the pod should crash or terminate or whatever, it would always make sure that there is at least one such pod running. But a deployment could also say, run me 10 replicas of that pod and organize everything that the service knows how to find this. But Kubernetes does a lot of other things. For example, node is something one should know. Nodes are the machines which are members of the Kubernetes clusters. And it manages secrets for you. So there's a lot of infrastructure into which one can plug. And obviously, the right idea is to get to know what these are, what are the right primitives to use, and then use them. So to get started, and again, you will know most of this, what you need a Kubernetes cluster. There's lots of ways to deploy these. And then there's a single command line tool called kube control to control that Kubernetes cluster. You can either run it on a machine in the cluster, or you can run it on your laptop and connect with the right credentials and so on. And if you have the right configuration and the right credentials, then you can talk to this. And it appears as if this whole machinery is one large computer on which you can start things. So let's quickly go through possibilities here. Maybe the easiest is that you can run Minikube on your computer. So you can have a complete Kubernetes cluster on one machine just for testing purposes. If you have Docker for Mac, then the latest version comes with Kubernetes support. So if you have Docker, you have Kubernetes as well. The other way is there's a tool called kubeadmin, which you can use to just take a bunch of machines, maybe some cloud instances somewhere, and make them into a Kubernetes cluster. There are some little challenges to this, but believe me, I'm not a Kubernetes expert, and I've done it after lunch today. No, that's not entirely true. I started before lunch, but it can be done. I have a 3-node cluster on which I will run my demonstrations. So that's actually a convenient way, but I will cover some of the challenges if you do it this way. Then, of course, all cloud providers nowadays have a Kubernetes offering, Google obviously, but also AWS and Azure. And maybe another possibility is you can just take 3 Raspberry Pis and run Kubernetes on it. If you want to know details, ask Devops. He does this all the time. So it's very prevalent. You can get your hands on it, and all you need is this kube control tool. Right. So how do you run ArangoDB in Kubernetes? So the idea is you essentially just tell it run a container, and that's it. And since one of our binary distributions is as a Docker container, as a Docker image, it is literally for any Kubernetes out there, it's just a single command, namely this one here, to run something. We will do this in a second, but obviously the question is, where's the data? Yeah, it's easy to deploy a container somewhere, but where does it keep its data? And what happens if that machine is restarted or if it's gone? Yeah. So these are interesting questions which we have to answer. Now let's do exactly that here. So this here is, no, where is it? Here I have a window which is just where I'm just logged in on one of these nodes. I could have copied the credentials here to me, to my computer, and run it there, but let's simply try it. I have a bunch of such YAML files here, and the first one I want to show is Arango single. And for those who have seen these things, it's probably quite familiar. I essentially deploy a single pod. I give it a name, some labels. I tell it what Docker image to execute. I do some kind of volume mounts. That means, in this case, I just store the data on the node where I run. I get some environment variables, and off I go. And with this YAML file, I at the same time deploy a service, because what I want is that ArangoDB instance is available on some port on all the nodes. That's a very simple thing. You see, it's a screen full, and it's just a simple command, compute control, create -f Arango single, and here we go. The resource description is taken from this YAML file. The resource is deployed with this command, and now things happen automatically. So for example, if I do get pod, I see that this ArangoDB single here is a single pod which is not yet ready. I don't care where it is, but sooner or later it will be there. And I can add get service. And yes, it deployed a node port service on port 30,867, which means that this network server, which is running on some container somewhere in my Kubernetes cluster, is available on port 30,867 on each node of my little Kubernetes cluster. That is probably not something you would do in production, but that's something you would do in development, just to be able to quickly fire something off. So the pod is running, the thing is there, so therefore I should, let's take this window, this is now my laptop. Let's quickly contact this. I think it's clear text. I've put the IP address of this guy here in my hosts file, and the port is 867. And I just do an AP version. And here we go. This shows multiple things. First of all, it shows the API of ArangoDB is just HTTP. That is the path under which one can ask for the version. And back I get just a single JSON object, which is the body of the result. And as you see, I can use either one of my 3 Kubernetes nodes. And what you don't see is that they all talk to the same container. So that is the way Kubernetes works. You deploy something, you get it, you deploy a service, you can access it, and that's it. You want to get rid of it again? Well, that's easy. Delete, and I always like this, just the same file, and it's gone. The service is gone, and the pod is gone, and here we go. That's my Slack, which we don't have to see, but here we go. Now that was easy, wasn't it? But what if this pod vanishes for whatever reason? What if the machine is rebooted? What if that machine fails? What if you need a larger database? What if you need a distributed database? What if you want to control where your storage actually is? Then things become a lot more complicated, and that is what keeps us busy for the rest of the talk. So storage in Kubernetes, just to give you an overview, is very manifold. Like you can attach a lot of different drives and file systems to a single computer, you can have a lot of different types of volumes in Kubernetes. You can just use an empty dir like I did, which says just grab some empty directory and some space on some file system on the node where you're running. That's of course not very durable. You can specify a concrete host path and organize your nodes if you do bare metal in the right way. But also you can use AWS Elastic Block Store, or you can use the corresponding thing from Google or Azure. You can use a distributed file system or whatever. Yeah? And all of this can be configured. Many of these volume types are attached, network attached storage. That means they are somehow available on each node, and you can just ask for them. It doesn't matter where the container is started. You can just mount it into the container. Everything is over the network, and that's fine. Isn't that great? Yes, it is, until you need the latest, the highest performance possible. And we, as a database manufacturer, say this isn't that great. So what ArangoDB, what a distributed ArangoDB prefers, is actually a locally attached SSD. But then, how do we manage replication and so on? Well, we have an answer to that. We don't need the replication and snapshotting and so on of networks attached storage, which many DevOps obviously like. What we need is the raw power of many IOPS. Yeah, we need very, very fast I/O. On the other hand, we handle replication, failover, fault tolerance, and so on the database level because that's our business. Yeah. So therefore, we have a unique challenge here. We are a distributed database. There's lots of volume offerings in Kubernetes, in particular, in different Kubernetes installations. There's lots of different such things. And we somehow have to make all our customers happy. And that will be interesting. So, since, was it 1.8? Kubernetes 1.8? Something like that. There is something called a persistent volume claim. So what's that? So I think people like Google have recognized this problem with storage, and so they have abstracted away the problem in a sense. If you are some application which needs persistent storage, what you actually deploy is a so-called persistent volume claim. And then something behind the scenes, some kind of operator, controller, or whatever, depending on your Kubernetes installation, goes away and satisfies this persistent volume claim by an actually persistent volume. And you can actually configure this outside of the deployment you do to get the right thing. So for example, if you are in Google Cloud and you deploy a persistent volume claim, it is automatically satisfied by some PCE persistent disk. If you are in AWS, it's automatically satisfied by some EBS. So in these proper cloud environments, you have automatic provisioning of volumes as you order them. But what about the bare metal? So obviously, we will have customers who say, no, I'm not going to the cloud. We have our bare metal servers, and we want to run Kubernetes on there. What then? How should this work? And so that is essentially the storage a distributed data store is faced. Now, let's do the next step. I, again, deploy just one pod, just to keep things simple for the moment, and one service, but I also deploy a persistent volume claim. And let's see what happens. Now, if I go to this window again, and I take my second YAML file, then it looks a bit more complicated already. So doesn't matter the details. And here we would have the deployment. That is something which keeps a single pod running all the time. Again, I just have to give the container image and so on. But I also tell it has a volume which uses a persistent volume claim. So again, I would deploy a service. That's exactly as before. And I deploy the persistent volume claim resource. Note that the deployment above references this persistent volume claim by name. So if I deploy these three things, and it's getting longer already, yeah, so it's no longer fitting on one screen, I can still easily deploy it, but it's not still so easy to write. So let's do this, kube control, create, and this file. There's a pod, not yet started. There's the service. There's the persistent volume claim. And the experts amongst you will know that if I didn't cheat here with my bare metal Kubernetes cluster, that persistent volume claim wouldn't be satisfied. And this pod here would not have started. And we get what I did here to cheat and to make it work, I'll tell you later. Anyway, let's do exactly what we did before. This time I'm running on the node pod, what is it, service? This time I'm running on the node pod 3966. And again, I can access this from my laptop on all three machines. And I get contact to the right thing. So the service is set up, the volume is there, it's in a persistent volume claim, and somehow magically it worked. The YAML file is getting a bit longer, but still it's okay. And let's get rid of it again. So that's what I want. I want somehow this abstraction of volumes. I want to be able to configure where it gets the volumes from actually. And where I deploy, I just want to say, use this persistent volume claim, somebody will satisfy it. That is going towards the right direction. This was the demo already. But it's getting a bit more complicated, and it's getting a bit more ugly. Now, what I showed you works as given on all these cloud platforms. It works on Minikube, it works directly on Docker, but on any if you just use kubeadm to deploy on some bare metal servers your own Kubernetes cluster, it wouldn't work. It would not have worked because I would not have configured something to satisfy these persistent volume claims. Now, obviously, we have only shown single server now. So what would happen if I had to deploy an ArangoDB cluster? Now, a small one with 3 coordinates, 3 database servers, never mind what they are, and 3 agents, forget about them for the time being. In any case, just the smallest ArangoDB cluster would have to deploy 9 pods, 9 persistent volumes claims, 2 services, 1 for internal access, 1 for external access. I would have to have deployments such that everything is nice and running and so on. There is another resource type called stateful set, which one could use, and so on and so on and so on. But if you think about it, all this would end up with a YAML file with not only dozens, but very quickly hundreds of lines. So it's all doable, it's all fine, but it's awkward. And it becomes to get a lot more awkward if you think about upgrades. If you think about, you want to do rolling upgrades, you want to change the images being used. Yeah, you want to scale up. You say, okay, I don't no longer only need 3 machines, I need to have 10 machines for this evening, and later I want to scale down again. Then you have to edit all these YAML files, and it's really awkward. As of the beginning of this year, this was the way to go. We had some bash script which produced a YAML file for a cluster. You could deploy that. It would start a cluster, all right, but it's getting inconvenient. And yes, you could say this is just the life with a distributed stateful application in a cloud environment. But no, we have to be better. Yeah? We don't want to make our customers suffer in this way. So what can we do? Fortunately, there's not only a complete zoo of different resources in Kubernetes, it's even better, you can have your own. There's something called custom resources, I believe starting with Kubernetes 1.9, or was it?
No, 7.
7, or even earlier. Anyway, that is, you can deploy your own. That is, you can create new things which can be deployed to your Kubernetes cluster. Now, you would do the following. You would have a custom resource definition, which you first deploy to your Kubernetes. Then this Kubernetes knows about this new type of resource. You then get full support from kube control. You can have YAML files which describe the instances of the resources you want to deploy. You can have something in the background, listen to them and modify them, some controller. And in any case, if you do that, if you do this pattern of creating a custom resource and have some controller in the background work with it, that is what is called a Kubernetes operator. And it's the latest and greatest in the Kubernetes world as far as I know. Obviously, development is very quickly. I think this was first done by CoreOS with the etcd operator, who have actually a very similar problem. Yeah, it's not quite the same because etcd installations will probably not grow and shrink as much as ArangoDB instances, and they have a lot of less different types of servers which have to be deployed. But essentially, they have the same problem. It's a stateful distributed application which needs to be kept running and upgraded and everything. And in actual fact, we have looked at a lot what they did and used the fact that it's open source. So wouldn't it be nice if we can simply install something on our Kubernetes cluster, and then we would have the resource type of an Arango deployment. Then we could have a very short YAML file which describes the cluster or single server or whatever setup of ArangoDB we want to deploy. We would use the standard workflow of deploying with kube control a YAML file to describe the specification for that resource type, and somebody magically would in the background do all this. And indeed, that is our approach. So all you have to do on a standard Kubernetes cluster, you take these 3 YAML files. That is our custom resource definition. That deploys one operator for deployments. And that is something else. I'll give you more details on it in a minute. That sorts out storage on a bare metal cluster. If you are in a cloud environment, you only need the first 2. So once you have done that here, you can just deploy a single server like this. Yeah, so that's now a 6-line YAML file which deploys a specific type of custom resource, namely an Arango deployment. The mode is single server, so that deploys a single server. So that's nice. And let's try it out immediately. Here is said file. So I've already deployed the operator, the storage operator, and the custom resource division to that Kubernetes cluster. But here in this file, I have a copy of that little 6-line YAML file, and I'm going to deploy exactly this to the cluster. Now, let's see what we have. Again, it's a single pod. Well, that's not quite what it does. This is a test balloon the operator sends off to understand what Arango version is in the Docker image I gave. It doesn't know really the version, because later when it wants to do upgrades and downgrades, it needs really to understand what's going on. So therefore, it starts a test balloon and sees what this is, and therefore this is already terminating again. Anyway, I think I can say this here, or I can see set Arango deployment to see that I have under this name an Arango deployment custom resource deployed. And that leads to the fact that there is a pod and what else is deployed. So there's the two services. One is internal and one is, what is this? One internal, I don't know, we have to ask Ewout afterwards. In any case, I have not very much, but in a uniform way. So what has now happened with the storage? And this is something I should cover. What is it? Storage. Yeah. So to make this work, because obviously I want to use the same abstraction as before in the example with the service, the operator needs some kind of storage to attach to these persistent volume claims. Now, to do that, I have not only deployed this Arango storage operator, but also I have deployed something which is described here. So I have deployed a custom resource of kind Arango local storage. So what's that? That's a second custom resource which tells this second operator, please take on all these nodes. Now, obviously, you could have selected a subset. On all these nodes, the file system /data, where I have made sure that there is a fast local SSD, and provide from that path persistent volumes which can satisfy persistent volume claims. So I have created an infrastructure exactly as Google did. Yeah? So Google provides with their letter-attached storage, box storage, and Amazon provides with that an environment where you can ask for persistent volume claims, and they are automatically satisfied. And so that is what we did. We used the abstractions for the persistent volume claim to make it so that the Arango deployment operator can do the same thing regardless on what kind of Kubernetes we are running, what kind of environment we have, and still get the right type of persistent storage. So that is, if you deploy such a server on AWS, you get block storage, unless you do something else. If you do it on Google, you get block storage. If you do it on Minikube, something automatically happens. If you do it on bare metal, and you have deployed our storage, then it's automatically satisfied with fast local SSDs. So that is somehow the trick we have done to satisfy all customers and yet don't complicate things. Because, let me just demonstrate. Yeah, so there's one more step I need to do, because now I have deployed that Arango instance, but I have not deployed a service. So we have talked about this today. I want to make this even easier, that this is done automatically. So what I need to do is I need to group control create -f Arango, no, CR single service. And now I can say group control get service. And I again have a node port, this time 30,529, to talk to these things. Now, why didn't we deploy this automatically? Well, because what you want depends on the circumstances. If you are on a bare metal cluster, very small, and want to test things, then you probably want to have a node port service. such that it's available on every node. If you are in Google Cloud and your Kubernetes cluster is 100 nodes, you probably don't want that. So there you probably want a kind of load balancer thing, which exposes your service load balanced under some IP address. So therefore, since we didn't know what we want, we didn't do it automatically. So therefore, you have to deploy it separately, and now it's available. So what I should now be able to do, and by default, we are now using SSL. So now I should be able to use this guy here and ignore certificates for now. And also we switch on authentication automatically. So therefore I get now an unauthorized. I reach my service, but I cannot authenticate. So what I need to do is I need to say user root with empty password. And here we go. I have contacted via SSL with authentication via the node port service this single Arango instance which was deployed with a local volume claim, a persistent volume claim. Right. So let's get rid of this again. Because you are now saying that's all fine, it was just a single container. Where is the meat? So this just summarizes how I deploy it, that I could ask for deployments, I could ask for ports and everything. Now, if I want to have a cluster, it's not more complicated. I just use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 line YAML file. Yeah? And I get a cluster. That's what I claim, with exactly the same amount of work as I did for a single instance, but now it's a cluster with 9 ports, 9 persistent volume claims, 9 times locally attached SSD mounted directly into the container, all talking to each other via some internal service, and in the end then exposed as a load balanced service. How would I pull that off? Well, it's really just this little YAML file. Or is it here shorter? 1, 2, 3, 4, 5, 6. No, it's the same. So let's watch this. It does the test balloon to understand the version of the database. It understands that this is version 3.3.5 of the database. And it initializes port, it's running. It's terminating because it has now understood the version. And now it's deploying the whole cluster for me. So whilst this is working, this will take 2 minutes or so. Let me quickly explain why we need so many services. To keep the configuration of the cluster, we run a 3-agent system called agency. That is essentially something like etcd. It's a highly available graph-based key-value store based on top of ArangoDB, which keeps the cluster configuration and the metadata about your collections. That is deployed in 3 different containers on 3 different machines, and it keeps everything together. That's always 3 or 5 if you need to be even more fault tolerant. So these 3 guys, they elect a leader, and the others are just replicas. Once the leader dies, you get an immediate failover to use any other follower. So that's our configuration store. You as a customer don't have to do anything with that. And then we have 2 types of servers. We have the primaries or the database servers, which actually hold the data and use the indexes and do the actual fetching of data and manipulating of data. And then we have the so-called coordinators. The coordinator level is the level which gets your cluster client requests, which knows about the topology of the cluster, which does the query planning and distribution of the query across the cluster, and then builds up a pipeline to fetch all the data from the database servers, put it together, filter in the right place, and deliver your result. Now it's interesting to be able to scale these independently. Because, for example, if you need more capacity, you probably want to scale the database level, database server layer. If you need more query power or more JavaScript execution power, then you want to scale the coordinators. In any case, the customer just has to talk to the coordinators, and therefore, now it's running, I deploy a service which just does a load balancer on top of the coordinators. So let's deploy that. Right. So this is the cluster service. It's again node port here, and it's again the port 30,529. So I should be able to do exactly the same here. Yep, it's again authenticated, it's again using TLS, it's again available on all 3 machines. Yeah, it's load balanced in the sense that this node port service is available on every node, and it distributes the requests across the 3 coordinators. So now we finally have no longer any single point of failure. The agency is highly available because it's a raft-based 3 tuple. And the coordinators are stateless. You can talk to any of them, and we have a load balancer in front of it. And the database servers are sitting there and storing the data. And as long as you configure the replication factor to be at least 2, you can use any one of them, and you still have all the data. Now let's play around a bit with this. Where do I have a browser? Here. No, this is 30,529. Yeah, I don't mess with a bytecode. You see, the load balancer load balances me between 3 instances. So therefore, now I have to accept 3 certificates. But once I have done that, why is that? Don't ask me why it's 4 times. And don't ask me why the CSS is not yet there. But here we go. We have hopefully working ArangoDB cluster. I think we are seeing some connectivity issue here. Here we go. There's 3 coordinators, 3 database servers. They are all up and running, and everything's fine. Now, I can even do things like click something in the UI to say I need another coordinator. Now, what has happened now? The UI of the database has stored that information in this agent, in this agency, and our operator is observing the wish of the user. And it's observing that I want another coordinator. So therefore, it knows to change the custom resource type of our Arango deployment, change some value in there, and change the number of coordinators from 3 to 4. So it deploys another one, and suddenly I have 4. The load balancing is all automatic because that's all done by the operator. So suddenly I have 4 coordinators. I think I cannot do plus here because I have only 3 Kubernetes nodes. But, and that's a bit of an adventure, I could do minus here. I could tell I only need 2 database servers. Now this works even if the data is distributed equally across the 3 servers, because what happens is that the system will choose one of them, make it empty. Well, one of them was empty, so therefore it was fast. It will empty out the data, replicate to other machines, make this server empty, and shut down the pod. This all works with the combination of the ArangoDB operator, with the changing of the resource definitions, and everything. If I now go back to my other window, which I lost, and I say group control get Arango deployment, here we go. And if I now say edit, example simple cluster, then you see that the actual internal specification is a lot larger, not too much larger, but it's not. It's a little bit larger. All the defaults have been filled in, but you see I have 3 agents. I have now 4 coordinators and 2 database servers. So if I needed 3, I could also just edit the configuration here back to 3, and should then see sooner or later another database server popping up here in the user interface. So it's all integrated with each other, and should so give a seamless experience for DevOps and people who want to deploy and use the database. This might now take a bit. You see, the user interface has found that it wants, well, that might actually be a bug here. If I change the deployment outside.
No, it works.
Yeah, it works. No, it's not a bug. It's all okay. So you see, it doesn't matter whether I do it on a user interface or whether I change the deployment of my custom resource, it just works seamlessly. And that is exactly what we want and what I believe our customers want. And again, I've just done it with 2 small YAML files, one for the cluster, one for the service, and we are trying to improve the situation even more by giving a possibility to specify what type of service we want to deploy it together with your cluster. Demo is already done. Yeah, this is something which I essentially have already covered. I've told you that to be able to use persistent volume claims on a bare metal cluster, I first have to have something which provides them. And in the cloud environment, this is automatic. In the bare metal environment, I have to deploy this Arango local storage resource, which is then automatically provided when a persistent volume claims comes up. So where are we with this? It is working. So that is actually quite incredible that we have started at the beginning of this year. We have released the 2nd release last week. It can be used. It can do deployments. It can do scaling up and down, even if there's data in there. You can do upgrading, and I'm happy to try this out in a second. You can tell it, I want to go to the next patch level by just changing the name of the Docker image. And it will automatically notice that this is a patch level upgrade, and will do a rolling upgrade and restart gracefully every one of your pods. And you can do recovery and so on and so on. But we do not yet recommend it for production. So this is really hot off the press. We are missing the integration of data center to data center, which is one of the next things we are doing. And there is so many configurations out there of Kubernetes with different network types, different volume types, different setups, and so on, that we do have to do a lot more manual and automatic testing before we actually say, yes, we recommend to use this in production. It's not that far away, so it's not years away. It's probably not even months, but rather weeks. And we notice that this is important, so we want to be quick there. But if you ask me today, don't use it in production yet. If you have some project which is a few months off with production, you can safely start trying it and play with it and see how it works, because by that time we will be ready for production use. So let's do one more little experiment. Where did I have my window? I noticed that I'm longer already than intended, but never mind. Let's try this upgrade thing. And since I'm already at the latest published version, let's downgrade. Because on the same patch level, this should actually work. Where's the name of the Docker image? This is. Oh, let's do it differently. Let's edit the cluster file. Let's. This is 3 already, and let's just. Oh, hang on. What's the name for the Docker image? Let's do it like I intended to do.
It's in the bottom of the page.
It's where?
So you want to scroll down.
Here we go. Latest, let's go down to 3.3.4. That's a bit scary. I didn't try it before. But, yeah, you see, there's an ID pod. That's the test balloon. It deploys the new image name. It takes the SHA-256 of the image, and it recalls which Arango version that is. And it should now notice that this is no longer 3.3.5, but 3.3.4. And once it has noticed that, it says, oh, customer wants a downgrade, but it's the same minor version, so that is okay. So what I would expect is that not only the test balloon is terminated now, but I would expect that one by one, these servers are now restarted in a sensible way. For example, it does the agents first. It knows that it is a critical thing to have 2 of them running at all times. So it first deploys the one which terminated new, and then does the next, and so on. This might take a few minutes, but here we go. Do we do a force pull every time?
Sorry?
Do we do a force pull every time?
No, but it has to pull the image on every
Because
machine.
it's a different version. Yeah.
So as soon as the agents are done, the other ones will be quicker because the image is already there.
Yeah. So let's wait. I find ways to talk during that time. And so the operator knows not only about compatibilities and incompatibilities. So right now it does a minor version downgrade, a patch level version downgrade, and it does a minor version upgrade if asked, but it doesn't do a major version upgrade because we reserve the right that this is not seamlessly possible without backup and restore. But you see, it's already doing the second agent, but now it's of course pulling on the second agent or the second server. This is done now. Oh, completed. I don't know whether I like that. Here we go, another init. Ah, yes, this is the third now. And so what we realize is that people do not only want to easily deploy a database, but they want to keep it running. And if you want to keep a database running and we release a minor patch level maybe every 2 weeks, it must be very seamless to upgrade without service interruption. So therefore, our thinking was that we need to provide something like this quite early on, such that people realize that running ArangoDB on Kubernetes is actually easy and convenient. So let's see whether Ewout's prediction is true, that it's now quicker. Yes. It still seems to do the third agent. Anyway, we can look in a few minutes. I can finish off stuff. This is all stuff which is pretty hot. We are in the process of doing that, but we are moving pretty quickly. And thanks to the environment, thanks to thinking of other people before us, and thanks to the open source character, and thanks to the good documentation of Kubernetes, it's actually eminently doable. So this was actually pulled off within 3 months or less. Or less than 3 months. 2 months, yeah. So custom resources seem to be exactly the right approach. It gives the right compromise of convenience and capabilities and convenience for our programming. So it is quite a lot of code, but it's not that bad. A lot of code can be automatically generated and so on. But of course, we have to keep an eye on things. Kubernetes is moving extremely fast. We don't know what the status of Kubernetes in a year's time is. Fortunately, all the APIs are versioned, and what is stable remains pretty stable in future versions, so that is okay. I've put some links here, and then let's have another look at how things are going. Here we go. It's now doing database servers. And we can watch this as we speak, because I'm essentially done with the presentation. Thank you very much, and I'm happy to answer questions and have discussions afterwards. Other questions? Yes.
The example you've shown us is basically 3 database servers with local storage each.
Yes.
So it's kind of local storage.
Yes.
So how, but at the beginning you also talked about shared storage like ClusterFS and stuff.
Yeah.
How would that change? Or would that change?
Okay. This deployment here wouldn't change a bit. It's the same deployment on the top level. Just the provider for the persistent volume claims, or for the persistent volumes satisfying the persistent volume claims would change. So on a Google Cloud system, you would not have to deploy our storage operator and the Arango storage resource. You would have to take care of that. You just deploy this one. You have your cluster, it's using block storage. Yeah, it's using persistent volumes in this way. However, technically, behind the scenes, something would change, because suddenly our containers, our processes, machines are no longer talking to local SSDs, but actually they are now talking over the network to attached block storage. And that works. It's secure, no problem with that. But depending on the size of these things, they might be faster or slower. Because if you share this storage with others, then you get a smaller contingent of IOPS, and then it becomes slow. And in particular, you have nasty effects, like for example on Amazon, if you test first and do a few little things, it is very, very fast, because you have this burst IOPS. But if you do this on a continuously growing basis, you suddenly see a very large drop in I/O performance, because then you have used up your burst contingent, and you suddenly are down to 3,000 IOPS. And if you compare that to 100,000 or 200,000 IOPS on a fast local SSD, then you see a huge drop in database performance. And yes, if you don't have that much I/O performance needs, that's okay. It might even be the better solution, because containers can be started all over the place. But if you need the highest performance, you are out of luck. And so therefore, we want to make this configurable for everybody.
Okay.
Further questions?
Okay. How does the whole thing work with distributed storage? Let's say we want to have ClusterFS or Ceph on bare metal. Does it work for now, or?
If you are on bare metal, then first of all, you have to make sure that ClusterFS is available here. Then you probably mount it under some local path on every node. Then you, no? Igor, please.
Okay, let me answer that. On ClusterFS, you would have a provider for persistent volumes with ClusterFS in your Kubernetes cluster. And that one takes care of the creation of persistent volumes for you. So then in that case, you don't use the storage operator that we provide, but you use the one that comes with ClusterFS for Kubernetes, and that is built in. And you would use that. The deployment doesn't change. You can specify in the deployment which kind of storage class you would like to use. That is an additional abstraction in Kubernetes, where you specify I want this storage class, and the storage class maps to, for example, ClusterFS or our operator or something like that. And if you specify the default storage class, if you don't specify anything in the deployment, it will use the default storage class. And if you have a highly advanced Kubernetes cluster with multiple storage classes, you can say, I want for the agents, I want global SSDs, and for the DB servers, I want something. Okay?
Awesome. Thank you. And so if I have different Kubernetes cluster and would like to do some kind of federation, so I guess it becomes more complicated. So, but if you don't, how could such a thing be supported? I guess it would be very hard to support such a scenario over Kubernetes clusters in different regions and so on.
As of now, the situation is as follows. One ArangoDB cluster can only exist in one Kubernetes cluster. That is a limitation of the database we have currently and of the operator. The only way out we offer is our data center to data center replication. Because what is easy with this setup is that once you have one ArangoDB cluster in some Kubernetes cluster, you can deploy a service which makes this or part of it visible to the outside. Yeah?
So it means I can live replicate my data to another data center in another region, and my applications in the other region can have access to my data.
Yes, but only read-only, and only asynchronous replication as we speak.
Okay.
So that's our offering. Cluster in one data center, cluster in another data center, asynchronous data center to data center replication with read-only support on the second data center. That is what we offer, and in the future it might be more, but that is what we currently offer.
Okay, but the main coordinator where the replication happens from the main or first region, what happens if the cluster is not available somehow, whatever, so for some reasons?
First of all, this whole setup doesn't have a single point of failure.
Okay.
So it's completely, also for the data center to data center application, it's a distributed fault-tolerant system. Yeah, so if any server goes down, then a replica is taken and everything keeps continuing. So obviously, you can have a service interruption of the whole cross-data center link. Then it will stop. You can monitor this. You can have metrics to indicate that. And after the network is reestablished, it automatically heals itself. What we currently offer that you don't have to have a full resync if the network is back after at most 1 hour. Yeah? In that way, it just seamlessly continues to work. After that, it does a full sync in the sense that it does a replication protocol which synchronizes all the data, but it doesn't have to move data over which is already there.
Mm-hmm. Great.
And you can form trees of these. So we had a customer who asked whether you can have both directions. No, you cannot have both directions between two clusters, but for example, you could replicate two different clusters, or you could replicate here and go on and so on. And obviously in the future we will improve things, but that is where we are.
Okay.
Yes.
Can I come back to this one cluster per database thingy? Mm-hmm. If I think of DevOps, what people do is like to have multiple databases per cluster. Just because they, I want to test this, and then
you can have as many ArangoDB deployments in the same Kubernetes cluster, but you cannot have one ArangoDB cluster be spanned over multiple Kubernetes clusters. But you can have multiple clusters as single instances in the same database.
Okay.
In the same Kubernetes cluster.
So it means I can deploy in different namespaces in the same
different namespaces, even in the same namespace, different deployments.
Okay.
You see, maybe I should explain this a bit. Yes, ArangoDB is a multi-model database, and one possibility is that you need fewer data stores because you can have multiple data models in one data store. But that doesn't make it necessary in a complicated system to have a monolithic database. Rather, you would have multiple different deployments. Maybe you need a single server graph database ArangoDB in one corner. And then you need a highly scalable key value store in another corner. You can use an ArangoDB cluster here and a single instance here. Or maybe you need something in between. So the idea is that you can have as many deployments of ArangoDB in your Kubernetes cluster as you wish. The only restriction is that one deployment must be in the same Kubernetes cluster.
Fantastic. And as I understood, Arango is also somehow an in-memory database.
That is changing. So we have two storage engines. The original storage engine we started with is the memory map files engine, and it was performance optimized for the case that all your data fits into RAM.
Yeah.
It is not stopping to work if you have more data than RAM, but it tends to swap and tends to be unhappy. But it is very, very quick if your data fits into main memory. And this is, of course, a serious limitation for database. So therefore, we have now a separate storage engine based on RocksDB, which allows you now to store as much data as you fit on disk. Yeah, so this, being an in-memory database, is essentially gone with the other storage engine. So depending on the use case, if you have something which wants to make use of all your SSD space, you should use the RocksDB storage engine. If you want the very least, the very best performance, and you have not that much data and maybe a large RAM, then you might want to use the files engine.
Okay.
But that's switchable, not in a running system, but at deployment time.
Okay.
But it's easy to deploy an files cluster and a RocksDB cluster in the same Kubernetes cluster if you want.
Ah. Great.
Okay, so what happens if a node fails? One of the Kubernetes nodes, it fails. Is the data replicated across all the remaining nodes?
Yes and no. It depends on how you configure it. Let me just show you. You just have to get connectivity again. So the idea is the following. What in a relational database is a table is a collection in ArangoDB because it's a document store. And we have multiple databases, but never mind. In any case, for every collection, that is for every table, you specify a replication factor. And you specify the number of shards. So if you, for example, specify 10 shards, then the data is automatically distributed across 10 different shards in your cluster. Shards reside on some of these database servers. Now, if you have a replication factor of 2, then the system keeps at all times at least 2 copies of every shard and automatically replicates in a synchronous fashion between the 2 copies. That is, every write you do on the database is going to both shards, both copies of the shard. Now, if you lose one database server, then every piece of data must be somewhere else because no 2 copies of a shard are on the same database server. So therefore, if a Kubernetes node fails, it hits at most 1 database server, and the system automatically heals itself because a new replica is chosen elsewhere, and the data is synchronized, and you have again 2 copies, and you don't lose any data. And all this happens behind the scenes without any kind of service interruption, maybe a short period of time for the failure. obviously, there's limits to this. If you specify replication factor 1, then you have just one copy, and if you lose that, it's gone. If you specify replication factor 2, and you are unlucky enough to lose 2 database servers, then if both copies are there, well, data is gone. So there's limits to everything. And so essentially, the usual setup would be a replication factor of 2, and then you can afford to lose one node without any service interruption and without data loss.
But those replicas, they're sitting on different servers.
Yeah.
But when you write, can you write only on one server or on both of them?
When you write, this is synchronous replication. When you write, the writes go to both. And it's only confirmed after it has been replicated to the other. So therefore, you sacrifice a bit of latency because it has to have 2 network hops to do the write.
From your application, you only talk to one server.
Yeah,
It
exactly.
also takes care of the rest.
Yeah, but from my application, I'm talking to one server, and if this server fails, then I'm automatically redirected.
So what happens is that your application client talks to a coordinator. And there's, in this case here, 3 coordinators, and your requests are load balanced across the 3. Now, if one of the coordinators fails, then it just retry it on another one, and you don't notice anything. Unless it is failed in the middle of your operation, and you might get one error, but the next request is okay again. But there's no data on the coordinators, so nothing is lost. If a database server fails, you only usually notice nothing because you are talking to a coordinator. That coordinator knows all the replicas, and it is writing to the right ones, and you don't notice anything. So that's the idea.
How does ArangoDB compare to other modern, let's say, databases like Cockroach, DB, Mongo, Redis? Okay, that's, as I understand, Arango is not a caching database, right? So it's more for large amount of data where you need persistence. It's a hybrid database where.
So let me give you.
Is there any or is the question perhaps is the question wrong? Can we compare Arango to other databases? What for advantages does it provide?
Okay, let me compare to a few of these players. And this is a bit of bragging. After all, I'm paid by ArangoDB, but it's not far from the truth. If you compare to MongoDB, I think we can do everything MongoDB can do with essentially the same performance or even faster. And we can do, in addition, if you use a single server, transactions, and even in the cluster, we can do joins. So as a document store, it's a lot more versatile with essentially the same performance characteristics as MongoDB. Also, I like the query language better. Now, if you compare to Neo4j, I think on a single server, we can do essentially whatever Neo4j can do, again with a different query language, but we can do it as well, and we can do the same performance. So that is all fine. But in addition, we are a distributed graph database. Neo4j is not really distributed. You can replicate data, and you can use multiple for queries, but it has to copy all the data everywhere. So we can scale out with certain limits. I shouldn't brag too much here, because if you shard a graph in an unsensible way or just any other way, then you might have, if you do graph traversals, you might have to do a lot of network hops. And that is inherently expensive. We have some answers to this as well. We have the smart graph feature, which probably would lead too far now. But in comparison to Neo4j, we can do a lot more distributed graphs and larger graphs. Now, if you compare to a relational database, we have, for a single server, like if you compare to a Postgres, we have the same kind of transactional guarantees because we have write transactions and read transactions and so on. And you can do most of the things because we do joins. You can do most of the things you can do with a relational store by just saying every table is a collection and all my documents look alike. And then you can essentially do the same as a relational database. But in addition, we can scale out and can do a lot of these join operations also in a distributed setup. So that's again an advantage. In addition, we can combine the three. If you compare with Redis, key value store, we can do key value. And I wouldn't say that we are only suitable for large data and are slower. Yes, we are slower than Redis because Redis is incredibly fast and essentially works best if everything fits in memory. But I would say we are not very far away, and it would have to be a very, very special situation where Redis is needed and ArangoDB cannot really play this role. But Redis is somehow separate. We cannot do anything. We cannot do everything Redis can do, and not as fast. But as you see, we try to play in a lot of different playing fields, and we can compete in many places. Now let's finish this off with CockroachDB. CockroachDB is great because it's distributed and it has distributed transactions. This is something we cannot do yet. If you have the distributed version of ArangoDB, the atomicity is on the document level. So you can do transactions which manipulate a single document. That's okay. They are completely isolated and atomic and everything is okay. But you cannot, at this stage, modify multiple documents in multiple collections in the cluster in one transaction. There's no isolation, and the atomicity is not given for multiple documents. That is an advantage Cockroach has, but they have only a single data model. And if you look at their performance, it is not really good. They have done a lot of improvements, and I'm not saying that it's a bad database, but I think performance-wise in the distributed setup, they cannot compete with this. But they have these transactions. And that is something where we want to grow into. So we have a plan to have distributed transactions ourselves, but this is a very difficult topic. And so maybe in a year's time, we might have distributed transactions as well, and can therefore also compete with something like CockroachDB. So that's the plan. And what I said is essentially true. Obviously, you will find the odd case where Neo4j is a bit faster with a graph, and where a Cypher query is more convenient than our query. You will find the odd case where MongoDB is a bit faster. You will find the odd case where Postgres is fantastically fast and doesn't use that much memory. Yeah? So that is all clear. But all in all, we can compete in all these playing fields. And in addition, we can support use cases where you actually need the multi-model nature and need the different data models in the same query.
Okay, last question from my side. Really, last question. So, what's the unique selling point for Arango for Kubernetes? So, from my experience, no database currently is so stable. Not Postgres, not Cockroach, not Couchbase. None of them is stable on Kubernetes because Kubernetes stateful set is very young, and our experience with load testing, none of them could get through our test. So why should one use Kubernetes to deploy, for instance, Arango on top? So today, I don't know, perhaps in 1 year, in future versions of Kubernetes where stateful sets are more better supported, perhaps it might be an idea to have Arango on Kubernetes. But why should I take care about Arango on Kubernetes today?
Okay, first of all, if you run Arango on Kubernetes, or deploy it yourself, we have a tool called the Starter, which makes it very easy to deploy on bare metal. Doesn't change very much for the operations of ArangoDB. So with respect to stability or whatever, it's essentially the same. You have some processes here, you have some processes here. We are not using the stateful sets, and so all the stability issues with respect to restarting and so on, it's essentially our operator who does the restarting of the pods. So that is why we don't recommend it in production, because it's only 2 months old.
Yeah.
But I think in a few months, this will be pretty stable, and I don't see a big problem. The stability as such is the same as the one you have with ArangoDB on other deployments as well. It's just a deployment option. From our perspective, it really doesn't matter whether you deploy on bare metal or whether you deploy ArangoDB on Kubernetes. It doesn't matter for us, but it probably matters for you, because most people use something like Kubernetes for easing the life of DevOps and for better resource utilization. So if you would choose to deploy ArangoDB yourself, then you probably dedicate, say, 10 machines to ArangoDB. If you have a Kubernetes cluster already, then you might want to fire up an Arango instance, do some development work, and later move this in the project to some productive use. Yeah, and it just is an option for you to do it in the environment you are already using. But with respect to the stability, I wouldn't say it matters very much. And obviously, we want to close that gap.
It's a very silly question.
Yeah.
What does the operator really do? Does the operator deploy a replica set or a stateful set?
No, it deploys pods.
It deploys, okay, good.
And as such, it's exactly the same as a systemd would deploy processes on a bare metal installation. It's the same kind of different isolation.
Yeah, okay.
And so therefore, there is, in that respect, very little moving parts between our operator and the actual container running. There's not much magic. It's just that it keeps an eye on things, it knows what to do, and it restarts, and it has, in addition, knowledge about how to do a rolling upgrade, how to do a rolling downgrade, and so on.
So basically, you built in the Kubernetes administration into your product.
Well, not all of it.
Not all of it, but
we use actually relatively low-level primitives of Kubernetes.
Cool.
Is that right?
Yeah.
And those resource types which have been there for a long time. Obviously, the custom resources we do ourselves, that is this mechanism. But
well, with custom resources, as I understand, the main reason where one should use that with your operator is not only scaling, but also the ease of use and deploying Arango on top of Kubernetes without having to deal with stateful sets, whatever.
Exactly. So the idea is basically, we know how to run a distributed database once it's running.
Okay.
We know how to deploy it. So therefore, we write the operator which does the deployment. What is missing, and we use very primitive parts of Kubernetes just to fire up pods, use persistent volume claims, and so on. But then, of course, we need an interface that you as a user can control the operator. And that is where the custom resource comes in, because that is the Kubernetes way, such that you have the same kind of use and feel like other resource types. It's just that you control it in Arango.
Cool. Okay.
Cool. Very nice.
Okay. If, for instance, if you only need a feature, maybe the graph feature of ArangoDB, is it possible to run the database engine for that purpose alone, or to optimize it just to?
Well, that is our secret sauce. There is no 3 database engines. There is just one. So you run it, you only use the graph feature, fine. But 2 months later, you discover that you might also need some document features. You can do that. There's no difference in deployment. You just deploy the thing, use it as a graph database, be happy. Deploy the thing, use it as a document store, be happy. Deploy the thing, use it as a combination of the 2, be happy. That's the message.
So all the 3 scopes run by default.
Yeah.
It's like you put different metadata on the same data.
In a sense, yes. So let me say a few words how this works. If you have a graph, what you have is you have vertices and you have edges. And most of the time you have some data associated with each vertex, and you have some data associated with each edge, which is just a connection between two edges, two vertices. So it doesn't really matter how you store that. A possible way is, for example, to have one table in a relational database, one row for each vertex, and another table for each edge. So how you store doesn't really matter. And what we do is we have a document collection where we have one document for each vertex, and an edge collection where you have one document for each edge, which means you can attach JSON data to each edge and to each vertex. The secret now comes if you do graph queries. The typical graph query is one where you start somewhere in the graph and explore the vicinity. You do the graph traversal. And now what you have to make sure is that however you have stored the data, you have to make sure that the operation to find all the outgoing edges from a vertex is extremely fast. That is what we do with a specialized edge index. So we put a certain edge index. Yeah?
Edge, okay.
So we index the edges in the edge collection such that this particular operation can find all the outgoing edges or all the incoming edges for backward traversals very quickly in time, which is in complexity, which is proportional to the number of outgoing edges. Not to the number of all edges, but to the number of all outgoing edges, which is best possible. And once you have such an edge index, and you have the graph traversal and graph query capabilities built into your query engine and into the query language, you have a graph database. And so therefore, it is not a different way to store the data. You store the vertices as a document collection, and you store the edges as a document collection. It's just this additional index and the additional query capabilities which make it into a graph database. And therefore, we don't have to run different personalities. We just offer a richer API to query things. That's it.
So you have several different indices.
Yeah, we have lots of different.
Graph and probably some linear, but all of these indices, they should fit in RAM.
Yes. In the MM files engine, all the indexes are in RAM. In RocksDB, they are all also stored in RocksDB because that's a sorted key value store. And we have very fast transactional cache facilities sitting in front of RocksDB, such that if you do repeated graph queries, for example, the list of outgoing edges comes from cache.
Can user create his own indices?
Not its own index types, but the user controls which additional indexes are created for the collections. So you can say, please create an index sorted by name and then last name. You can even say, create an index which is first sorted by the from entry of the edge and then by some timestamp. That allows you to do vertex-centric indexes and so on. So you can control that, and that obviously decides about the final performance of your queries. And we have geo-index, we have whatnot, sorted index.
I have one more question.
Very last.
Okay, let's say I would like to migrate from Mongo to Cockroach. How painful is it?
To Cockroach
or how easy is it to migrate from other databases? Let's say
if you have
NoSQL, Mongo. How does it work? Is there an interface tooling?
Yeah. So we have a very fast import utility which can either take JSON data or comma-separated value. So whatever you do, you just export to a bunch of JSON documents, you export to comma-separated values, and then you track it into ArangoDB. End of story.
Easy. Okay. Good. Very nice. Thank you.
And for the performance metrics, what do you have? Can you plug it with other metrics like InfluxDB or Prometheus?
We have good support for the data center to data center metrics for Prometheus. And as we speak, Ewald is writing an adapter which takes the JSON metrics we export as statistics over the performance and exports it in a Prometheus format. And we will make this very easy in Kubernetes, such that you can just switch it on. And then every single database server has a sidecar container which exports as Prometheus. So that doesn't cost performance and gives you Prometheus metrics right away. Good. Let's stop here. We have still time for chat and further questions.
Okay. Thank you very much. And thanks all who